Good morning, ma'am. Yes, ma'am. Thank you. You got Saturday in this NEPA.
Good morning, everybody. We have some minutes back, but it doesn't matter. It's a 2-hour lecture, so we're going to move well. Once more, I say good morning. You're welcome to today's Thursday, the 9th of March, 2023 lecture on Chemistry 176. Thank you for making your time with me. The class is still very few. I'm expecting almost times 10 of what I'm saying. We are not up to 200 yet. I don't know why you have decided to abscond from this lecture. Now I'll start sharing my screen and make sure you check the chats and you see the YouTube link. Make sure you copy it immediately. So we continue from where we stopped yesterday. I gave you this assignments. How many of you did it? Not too sure, but I feel you should have done it. Should have done it. If you did that assignment, bring it out and mark yourself. Just be faithful. I hope you'll be faithful. Okay. So the answers are this. Did you get this? Oh, it was supposed to be a homework. So let me quickly change it to homework. Good. So should have done that. Now we were on reactions of carbonates, and we have done quite a good number. I gave you this when we were there. We were on reactions. We have done it up to the Grignard reagent number 4. So we have number 5 to go through. There were some reactions on my Gmail, I think specifically from yours, Governor, and also Bosse. I think one of your reps. Let me see, she was actually asking what's that there are some slides I did not mention or we didn't lecture ourselves on. No problem. I'll surely show you, but there are things I don't expect you to take cognizance of as such. She was first, before I come to this 177, let's check on 167. She was saying, yeah, you will see that I marked it X in red. So when I mark things in X like that, maybe it's not for your level, or I don't want to bug you. The most important thing is that there is oxidative cleavage of alkenes called ozonolysis. Simple thing, yielding carbonides. It was under preparation or synthesis of carbonides. And then what is important there was what I explained, that immediately you have your ozonolysis number 1, you have your ozonide being produced. That's why I went to 168. And the breakage will yield the respective carbonides depending on the structure of the carbon-carbon double bond. If the carbon double bond, if it is still bonded to an hydrogen, it will yield an aldehyde. If there is no hydrogen bonded to that carbon-carbon double bond, that particular carbon will yield the ketone. I think I said all this yesterday, so let me not over reverse. What I'm trying to say is that 167 she demanded is no big deal. She should just forget about it. She was saying 178 or so again. It's just a common thing. You can see I place X, so it doesn't waste our time. These are things I've said. Definitely everybody knows these are aldehyde. Anytime you oxidize aldehyde, it will come to carboxylic acid. That's the oxidative trend. We have done that. You have a primary alcohol, it yields an aldehyde. The primary alcohol yielding aldehyde will not stop at that oxidation. In the presence especially of chromium compounds, you will have further oxidation of that aldehyde to the carboxylic acid. So it's not a big deal. You will recall, that's why I said recall. If you check on those slides, I don't confuse you, it's just to tell you, you can see that. The 182 has an X, just to explain the aspect of Tolin's reagents and try to see the chemistry behind it. That how do we prepare it? You have addition of ammonia to your silver nitrate is quite an expensive chemical. And this reaction, ammonia added to silver nitrate, converts the silver ion to a diamine silver 1 ion, and that's the complex that's so the what we really refer to as Tolin's reagents, which I don't think you have to write, is the ammoniacal silver nitrate. That is the what is more important is this last statement that aldehydes are good reducing agents. So you should take note of that. So that is why they are easily oxidized to acids. They don't need any special catalyst. And it distinguishes it. These silver nitrate Tolin's reagents reaction. Ketones are hard to oxidize, and that's why you don't have much of it. She was talking about 185 again. 185, what is 185? It's just I think I did this 185 where it was the classwork when I said, okay, I write out the condensation derivatives forms from the reaction of each of the following. In fact, I'm changing it to a homework. I talked about the theory so well, and I believe you should have it. You can always have that. It's not a big deal. Not a big deal. No problem. So we talked about these ammonia derivatives, and we had talked about hydroxylamine. These are reactions, under reactions of carbonides. And I said what it will result to give. We have done this, if you recollect, hydroxylamine will result to give the oxide. So I paraphrase it as A and G. But now in this question, it's now giving you specific examples. This is what? How many carbon? This is a 2-methyl propanol. So if it's a 2-methyl propanol, that is, if you have it here, that's the carbonyl. It means one of the A's, A or G, happens to be a terminal, that is aldehyde, H, and the second one is this moiety. So if it's related, just go back to this equation for the hydroxylamine, it will form the oxide. So the oxide will be such that you have that 2-methyl isopropyl moiety with this, where the Y is our OH. It's just for you to practice. So my dear person, go and try it more. There is nothing I give you here that is below your standard or that will yield you to be confused. So we start today's lecture. We start today's lecture by continuing from where we stopped. Like I told you earlier, this is reaction number 5 among the list I gave you. The list I gave you is a little lengthy. Why do I even have the list again? a little lengthy, but we are now on number 5. We have treated in quite a good number of them. So this morning we're commencing on looking at reactions of carbonides with alcohols. And I've given the summary that it yields acetal, and which is used as a protective means. Let's go there so that we don't start bitching about it. Let me say quickly that we have treated 1, 2, 3, 4 in details on the reactions. I even gave you this as an assignment, renal revision. I'm giving you specific renal revision, which I believe we did religiously. And this morning, this was the assignment I gave you home yesterday, and I'm also giving you the answers. Okay, mark yourself. Did you come out with something like this? That's you. So, class, we are continuing in the reactions of carbonides, and this time around, the chemistry of carbonides in its reaction with alcohols. Alcohols, like you know, are carbon bonded to OH, like that. So anytime this is a general reaction where your carbonide is reacting with the alcohol to give the acetal. The acetal is a diether. The first homologous series we treated were ethers. Ethers are characterized with carbon, oxygen, carbon, bond. So you have 2 of those bonds. We have 2 of those bonds here. We have COR, another COR here. So that's why we call it a diether. So over here, it leads to acetal diether formation. The reaction is mainly for aldehyde. Please take cognizance. A or G must definitely be hydrogen. So it's the terminal carbonate. So in fact, the aldehyde easily adds to alcohols once your reagents are dry. And HCl can act as catalyst too in this kind of reaction. Definitely, you don't expect me to be asking for general reaction in exams. R could be anything. If it's a methyl, just replace this one. That's a methoxide, dimethoxide form of your aldehyde that you started with. So it's not a big deal. Yeah, in fact, I have a vivid example. This is ethanol here. Ethanol is reacting with 2 molecules of ethanol. Great. So it's not far-fetched. Just cool your brain, pour some little cold water on your brain after you've eaten well after the lecture, and try to see, is this true what this professor Mrs. has given us? And you see that it will be true. Most common is the addition of ethanol to ethanol to give the ether that is named as 1,1-diethoxyethane. We normally refer to these as acetal. These are protective groups. You don't need it for your level, but in synthesis or reactions in organic chemistry, you use acetals to protect maybe like these some functional groups, so that it doesn't participate in some steps of reaction synthesis. And then when you now finish, you just perform hydrolysis and you remove the protective group. So, but that is not, we're not going deep into those things. Like I said, what is majorly or germane here is that this is a very good example to show the addition reaction of aldehyde with alcohol. So addition reactions, and this time of aldehyde, let me put it, of aldehydes with alcohols, because specifically we want it to be alcohols. Okay. It's not a big deal, it's not something you fidget about. We have that immediately. Okay. Now the next set of reactions number 6 to 9, are reduction reactions of both aldehydes and ketones. Like I said initially, they are characterized. They have that significance or importance of either you use them to identify the particular carbonide crystallizing out of whatever. So reactions 6 to 9 are actually reduction reactions. All of them. I remember this. Number 7 is paramount. You are going to meet it in your chemistry 191. Same thing to your Iodoform test. Iodoform test is an important test in your chemistry 191 practical. So please listen very well. Get your jotters near you. Clemmensen's reduction is very common. Very common. How you turn CH2s to carbonize. When we come there, you see the reagents. Zinc amalgam. Make use of that. So coming back to that reaction number 6 to 9, as we indicated, 6 to 9 are reduction reactions of the carbonate. And we have said our carbonite, we have our aldehydes and our ketones. So the first one there is the reduction reaction utilizing lithium aluminum hydride, or in other words, you can use hydrogen in nickel. So aldehydes and ketones can be reduced. You know, it's like a backward reaction. Oxidation, we have seen oxidative trends. If you reduce aldehyde, what do you expect? We get a primary alcohol, a reversing back. If you reduce ketone, we have what? We will have a secondary alcohol. So what yielded those things is the oxidative trend. Primary alcohol yielded us aldehyde. So if you now reduce aldehyde, you go back to your primary alcohol. With the oxidation of a secondary alcohol, yielded us ketone. And you are used to this. If they wake you up from it, you should be able to say that. And even though you don't praise me, but you should, if you don't know it before, or if you've known it before, I'm hammering it on you again. You can have it, depending on the reagent you have, you can have it the backward product or the forward product. So over there. So just depending on our reagent. If it's an alcohol, we want to bring back it, then we'll use something like a chromium compound, and then you can be sure this ethanol will yield ethanol. So, but with a reducing reagent, you have the ethanol yielding ethanol, and whatever that will be. So we have that. Let's see other examples. Even if it is an aromatic aldehyde, like benzaldehyde, just reduce the lithium aluminum hydride, yes, maybe in acid. Once you have something like that, so we have this benzaldehyde undergoing reduction to give phenylmethanol, benzyl alcohol. And then we have our propanone, which is an example of a ketone. You can see it's the secondary alcohol that it yielded. So, sorry. Okay, so I continue I'm also giving you time so that you can copy your, even though you have the duty, but you can always copy your jotter and you have it there. So these are few examples. Anytime you have benzaldehyde reduced, you have a primary alcohol. Anytime you have a ketone reduced, you will have a secondary alcohol. So it's very straightforward. Now, reaction number 7. If I say it's germane in your practicals, reaction of this aldehyde, utilizing your Fehling solution. So, reaction with Fehling solutions, aldehydes are capable of reducing copper 2 to copper 1 here, and you have coloration here. So it's easy, the qualitative analysis. You easily score your 100% of the mark. Alkaline solution of your copper 2 tartrates, referred to as our Fehling solution, is royal blue solution. So by the time you now warm it with your aldehyde, you will just find some yellow crystals coming out, orange yellow precipitate, and that confirms this is an aldehyde. So it's a very germane reaction for confirming aldehyde. So it's used, I'm going to put it in red so that we know that is what we are set out for. It's used in confirming presence of an aldehyde. Yeah. Okay. Let's continue. Number 8 reaction is also unique. The Iodoform test is for identifying ketones, not just any ketone, methyl ketones. In the Iodoform test, ketones are less easily oxidized, but it will, it's a very germane and important reaction for identifying our Thank you for telling me I'm muted. No problem. I'm trying to regulate some things there. Okay. So I'll go to the next slide that explains the Iodoform test better. Now, we know that comparing ketones and carbonates, ketones are less reducing agents, or rather, they don't oxidize easily. They are difficult to oxidize. But a very good oxidation reaction of ketones is this Iodoform test that makes it. Sahid Abdul Muiz, what is your notion? What do you want to tell me? Please don't disturb my class. You are coming in, maybe. No problem. Once you are coming in, just sit down where you are. Take out your daughter and join the class. For those of you that are just coming in, I'll try to see if I can put okay. What's your direct message? Stephen Austin. Please don't disturb this class. Though. Let me see if I can give you. You'll see the link on the chat. Stop disturbing my class, please. So, though ketones are difficult to oxidize, the Iodoform test is a peculiar, a unique oxidation reaction of ketones that is very useful to identify them. In fact, specifically, this reaction is used in identifying methyl ketones. That is, when one of the arrows that are linked to the carbonate is a methyl group. So, a 2-ketone, a 2-one is what we use this Iodoform test. So, it is given by methyl ketones, such as your propanone, butanone, likewise ethanol, and ethanoyl moieties. These ones we also Iodoform test, we recognize them. So solution of iodine in sodium hydroxide is warmed with our propanone, that's our methyl ketone, and the solution has iodates 1 ion, as it, IO minus, which acts as the oxidizing agent. That's the iodoform. You can see it here. That's it here in the equation. The equation rounds up all I've been saying. And then you know, so the iodates 1 ion act as our oxidizing agent, and then you can see the precipitation of our triodomethane, which is responsible for the yellow precipitates. This is a very germane equation. I can ask 191 even in 176 question. So these are good qualitative analysis. So 6 to 9 are very important reactions. Please, they usually 6 to 8. Now, I've told you all of them are reduction reactions, and you can prove why it's reduction reaction. All those, you can calculate the oxidation state, and you see that it's a reduction reaction that is proceeding. Now, the last one is 2 in 1, though I normally don't teach this. Why? Because I feel maybe it's for 300 level students, but I think if I can give you a hint, I think 1 or 2 times, some of my professors that taught me, I said, Orokola, you are teaching these students heavy things, but I said, no problem. It's just to make them strong. Let me just briefly touch it. In this set of reaction is a reduction reaction. The reagents, they are similar, but the reagents are different. The above 2, that is the Clemmensen's reduction and the Wolff-Kirchner reduction, are 2 of so many effective methods for reducing ketone carbonyls. You know, we said ketonic carbonyls or ketones are not so active, but these reactions are germane, they are beautiful. You will notice here that the ketonic carbonyl is being reduced to methylene. What is methylene? Methylene is CH2. Can you see? Here you have a CH2, a CH3, and then the carbonyl ketone. What is it reduced to in Clemmensen's reduction? You have the carbonyl C double bond O reduced to CH2. I can give you this reagent in the exam. Zinc amalgam, that is zinc mercury, that's what I'm calling. I can put Zn/Hg. Zinc amalgam in any dilute acid, or just write the name Clemmensen's reduction. Predict the product of this ketone undergoing Clemmensen's reduction. Just look for where the carbonyl is, and you have your CH2. Once you have your CH2, you give the product. Look for alternatives. Good. They are making you people jam bites. You still have to go through objectives in your final question. So you can easily score. I've seen students scoring 90%, 95%, in 170. And I still have some students scoring 15%, 10%. May that not be your portion, but make sure you always come to my class. So the other one is just like it too. It's changing it to CH2, but the reagent is different. Over here is making use of hydrazine. You can recollect your hydrazine, we treated it yesterday. So in basic medium, hydrazine basic medium, the discoverers they are the first people to use this reagent to perform this suspension reaction. And that's why it is named after them. Whether you call it zinc amalgam in dilute acid or you call it Clemmensen's reduction, no problem. They are still on the same line. So just changing carbonyl to CH2. And whether you call it Wolff-Kirchner reduction or you said hydrazine in basic medium with little heat, the 2 of them little heat, you have your carbonyl change to CH2. So reading through, Clemmensen's reduction is utilizing acidic solution of zinc dissolved in mercury, that is zinc amalgam, as its own reducing agent. Whereas Wolff-Kirchner reduction is employing hydrazine, that's it, NH2 twice, H2N, NH2 in basic medium. So recall we used above this under basic medium. I've treated it earlier. So everybody clap for me where you are. Great. So I'm going to give you this. I won't call it a classwork. I will give you this as an homework because I won't give you the answer until next week, maybe, or until exam period. What will reactions of zinc amalgam in HCl I may decide to remove the Clemmensen's reduction with each of the following. I'm not asking for Wolf Krishna, that is this one, Krishna, but at least the Clemmensen's reduction. All your seniors know so much about it. So if you pick a benzaldehyde, you say we are not interested in that. But butanol will work. It will work for butanol, it will work for 2-hexanol. That's very good of me. So let me move straight to another aspect. We've actually treated carbonates, and we have used so many hours to treat these carbonates. So we're coming to another homologous series of compounds, and we should be moving to the end gradually. I believe by next week, you should have finished with me, and I believe you enjoyed my class. But notwithstanding, let's just move on to this last one. This last one is very, very, very important because they are a group of compounds we are used to. They are common in the laboratory, and you will see them. We will still treat them under the perspectives, general information, introduction. We also go through some very important things like their nomenclature. How are they named? We also So we'll be treating their general introduction, how to name them. Well, I placed done earlier. Let me remove it. It's not done earlier. I'm just going to do it now. So then we look at their importance, uses, applications, importance, uses, applications. In fact, there should be one more. I see properties. Properties, yeah, their properties of the carboxylic acids. So we have that also there. And immediately we finish properties, we come to their synthesis, their formation, that we call it formation, synthesis, and whatever, and preparation is still the same. Formation. So we have all these to treat. And another germane thing, chemistry and reactions of carboxylic acid. Yes, I put it in red question because I know you have done it even in your secondary school. So then there is another beautiful aspect. And it's like I'm touching another homologous series of compounds, the derivatives of carboxylic acid. I'm going to choose here. So quickly, we start. Let's talk some general stories about this carboxylic acid. We get more used to them. Also, you'll be hearing of carboxylic acid from your GS, not even essays. And in your WAEC, we did some of this, even practical chemistry now in O level, WAEC, JAMB, and also others, GC and the rest. They are asking questions on carboxylic acid, and they are a practical aspect of organic. So just go and build, we're going to build on past knowledge. Carboxylic acid are a class of organic compounds. Carboxylic acids are a class of organic compounds that have the carboxyl functional group COOH. I know you know that already, which is good. That is, the carbonyl is there, and also the hydroxyl. No wonder their name, in aldehyde too, I said alcohol that has been dehydrogenated. Don't worry. I love using some terms that will make you understand. That's the more important thing. Please, governor and class reps, make sure you people are not missing classes. You miss a lot of classes, and I'll start giving you impromptu tests, even on this platform. So expect my test anytime, and you are not to giraffe. So each individual should be able to go open and chat, present, give your attendance on the chat individually. I don't know why you people love logging up, and 3 of you are there. like I said, that's where their name is. They said carboxyl, carbonyl, then hydroxyl, just combining the two. But everybody say but where you are. But the funny thing is these are two distinct functional groups. Carbonyls, which we have treated, ketones, aldehydes, at least I've treated it into detail. The hydroxyl alcohols, though I'm not to teach you alcohols, I guess Dr. Oloyede will be teaching you that in detail. But these are two distinct functional groups. Because the funny thing is that the characteristics, the features, the properties, the reactions, the preparation of carboxylic acid is quite different from ordinary or carbonyls or hydroxyl. Neither is it combining the two. So the two groups modify each other such that it results to fresh chemical reactivity for the carboxyl group. Each of those reactivity are quite different. They don't resemble either of carbonyl or either of alcohols. So they does not resemble either of the two constituents as separate entities. So the more reason you have to listen to this lecture so that you understand it better and you don't confuse yourself thinking because there is a carbonyl there, and now on practical side, their saturated homologs are referred to alkanoic acids. We are used to that, and we have this general formula, which you are used to from the GSS, like I said. They are also referred to as fatty acids, very important systems in the natural product. You can obtain them from natural sources. For instance, in our palm oil, you have this active palmitic acid, hexadecanoic acid, and its derivatives, especially the unsaturated ones, like the oleic acid, so beautiful for our freshness. Antioxidant, it makes us anti-aging, it makes us beautiful. So we have stearic acid, which is octadecanoic acid, and so on and so forth. Then the most common of this carboxylic acid is the second member, which is ethanoic acid. Ethanoic acid trivially is known as glacial acetic acid. Though trivial, but I told you trivial names are quite welcome in organic chemistry. So on the chemistry of carboxylic acid, why is it totally different from ordinary carbonyl or ordinary or 100% alcohol? Is because of that combination. And that combination now yields some of this summary, which I'm going to give you. Well, I'm going to show you the structure of carbonyl very soon, and which I know you are used to. Then they easily undergo hydrogen bonding. And you can see that because on their structure, you have this OH bond that can easily bond. And I've told you this carbonyl bond is polarized. So let's just move on systematically. We come to their properties, and then for their preparations and synthesis, we check on their industrial and commercial sources of obtaining them. Then for their synthesis is quite, in fact, if you close your eyes, you can give me this one. We have talked of aldehyde being oxidized to carboxylic acid. We have talked of that earlier. So whenever you have a primary alcohol, it first oxidizes to aldehyde, it doesn't need you to beg it. It will proceed straight to forming the carboxylic acid. So then we talked of, in the preparation, we'll be looking at how you can obtain them utilizing the Grignard reagent synthesis. So Grignard reactions involving carbonations. Then through hydrolysis of nitrite, hydrolysis of esters, involving saponifications. Oh, there's this beautiful one that they also tell me that is above your level. And I don't think it's above your level. Cannizzaro reaction. Through Cannizzaro reaction, so germane and beautiful, you can write it down and run. If you don't get, we don't get there today, we will definitely get there early next week. So we have Cannizzaro reaction too, in their preparation or synthesis or formation. Then how we can have some aromatic carboxylic acid, especially a very common simple one, which is our benzoic acids. You can easily oxidize methyl benzenes and its derivative and get your benzoic acid, better still known to as benzene carboxylic acid. Then we will be ending the chemistry of carboxylic acid, looking at their general reactions. I've been showing you some things about it, and you understand it better. I believe by the time we're here, we should be saying we are rounding up my aspect of 176. So we look at roles, effects, and importances of the medium on acidic properties. That is things like their salt formation, reactions, esterification, their involvement, reacting with alcohols to form ester and water only, a reaction you have known in your, I can almost say primary school, GSS, esterification reaction. We have halogenation reactions, conversion into ester chlorides, reductions, amide formation. These are some reactions we look into their chemistry, checking some equations to support in that perspective. And like I said, another set of homologous series on itself, derivative of these acids. There are 4 in number. I want us to see there are more than 4, but we'll be considering the acid chlorides, acid chlorides, the anhydrides, the esters, the amides. You can write this 4 down so that you are used to what are their functional groups, how do they look, what is the structure like. You know, you can pick them up from maybe the subtopics I have here. So based on the structure of carboxylic acid, like we said, we have carbonized system, but like we treated in aldehydes and ketones, that is the carbonized. There is a kind of mesomeric withdrawal of electrons away from carbon. I've said that there, towards the more electronegative oxygen. So in the carboxylic acid, the carbonyl bonding therein leads to a kind of relatively positive charge on the carbon of the carbonyl, and the oxygen is slightly negative. So electron deficiency of carbon in the carbonyl is also results in inductive effect apart from the mesomeric withdrawal of electron. So you now have that polarization, and that's the structure that shows you what is actually happening here. So you have the inductive effect and you have the mesomeric effect, which you have treated under the carbonyl. Now, still on structure, this is the testifies the stability of the carboxylate anion. I want you to take cognizance of this carboxylate anion. It's germane when we are looking at the chemistry reactions of carboxylic acid. What is the carboxylate ion? That is a deprotonated carboxylic acid will give us our carboxylate anion. Anion is a negative ion, so that is where you have it. So therefore, enhancing removal of the proton. You will not observe this in alcohols. So that's why his own chemistry is different from alcohols. It's even more difficult to remove hydrogen from alcohols. It will really cry on you and shout on you that don't remove my hydrogen. Alcohol doesn't like proton removal, whereas carboxylic acid easily do that. Hence, they have weaker acidic property when you compare them to carboxylic acid. Well, I'm sorry. I love teaching people to know what chemistry is and the application of chemistry, and not just memorizing chemistry. So understanding chemistry is my desire. So the second bullet says the carboxylate anion that is formed here exists as resonance hybrid. And I'm going to show you the structure very soon, where you have the pi electrons being delocalized about the 2 carbons to oxygen bonds. So making a kind of dimeric molecule, so to say equivalent, and you call it the carboxylate ion. Everybody say that, the carboxylate ion. That's it here. We are coming to a germane aspect of this. It's actually, it flows. You can see a back front arrow here. That means this molecule is equivalent to this molecule and can be better represented as saying that the double bond flows between the 2 oxygens. That's the minus there. So, you know, when we were here, I said hydrogen bonding. That's the second bullet here. And that's what I want us to look at and see how this affects carboxylic acid. So very, very germane chemistry of carboxylic acid is hydrogen bonding that is common to them, that is germane to them. The simplest carboxylic acid as the first member, methanoic acid, and the second member, glacial acetic acid, better known as ethanoic acid. They exist mostly, in fact, majorly as a dimer. How is this brought to pass? It is like this. It's quite simple. If either R's are hydrogen, when it's hydrogen, that's methanoic acid, or the R is CH3, that is ethanoic acid. So you have two molecules of it dimerizing through the formation of hydrogen bond. This one turns upside down to this one. So you have the hydrogen bondings for the two molecules, making them to be dimerized. And it has influence on its chemistry, on its properties. So you have it in the dimeric forms. The highly polar carboxylic acid dimerizes in liquid phase and in non-aqueous solvents like your tetrachloromethane, forming two hydrogen bonds between the pair of molecules. The structure I have shown you. So what's the implication of this one? The ease of dimer formation in carboxylic acid is what is responsible for the observed extra high boiling point for carboxylic acid, especially when you are trying to compare it with alcohols that have similar molecular mass. In fact, it is as much as 20 degrees higher. And I'm going to show you with this table. If you go, you can write the table down and go and verify. If you check on your ethanoic acid, the equivalent alcohol is propanol, propan 1-ol. Both of them have molecular mass, relative molecular weight of 66. But look at their boiling point. That of the acid is 118, whereas that of the propanol is 97 degrees C, which is about 20 degrees different, even though their molecular weights are different. So can you account for this difference? What accounts for it? It is the hydrogen bond, the dimerization that ethanoic acid will undergo, which is not seen in propanol. The same thing applies to these two examples too here. Over here, I have propanoic acid. Propanoic acid has molecular weight of 74. And also I have, what is this one? This is butanol. Butan 1-ol has molecular weight of 74. But the boiling point of your propanoic acid is 141, whereas this one is, the alcohol is 117. It's about, in fact, more than 20 degrees different. So that is what is germane. The hydrogen bonding, the implication is that with alcohol having similar molecular mass, it has higher boiling point, in fact, as much as 20 degrees or even higher, like I've said. So in water generally, other hydroxylic solvents, the dimers dissociate into their monomeric forms, unlike carboxylic acids. So let's come to, I've spoken about those elementary chemistry of carboxylic acids and what we observe over there. There's a question here, let me see. Yeah, Shonawo Ayomide, good morning, ma. Please, I would like to know why groups added to the left side of the compound are most times in the opposites. What do you mean? I don't. For example, hydroxy turns to, okay, OH turns to HO, and CH3 turns to H3C. It's still the same. Still the same. If you say carbon, it's an ethanol now. Let me just explain to the class. Answer line. Okay. Let me just answer to everybody. Whenever you have an hydroxy group, alcohol, yes, it's better to write it carbon linking directly to oxygen, and that oxygen bonding to hydrogen. So we have COH. You don't write it as CHO. If you write as CHO, you are referring to aldehyde. But if you have written your C on the right side, then you could have, and you want your OH on the left, you could write it as HOC. The C is still bonded to O before O to H. So it's still the same. Then for the CH3, if I'm even using something like ChemDraw to draw, and of course, this carbon of the CH3 is bonded somewhere. It must always be there. If it happens to be on the left side, carbon will still be bonded to maybe a benzene ring or whatever, aromatic ring. Then, since it is not H3 that is bonding to the aromatic ring, carbon will be bonded to the aromatic ring, and then anywhere around that carbon, I can put at the back, the front, whatever, of the carbon. But I never write CH3 now linking to the benzene ring. The link should be from the carbon. So whether it's proton, it's like you are looking for longest carbon chain. Whether you are counting the carbon chain up or down, left or right, longest chain is longest chain from your so please don't be confused. You know, I guess I've answered your question. Let me just close the aspect of questions, and then we continue our lecture. It's nice she has asked that. You don't need to be confused in my class. Even when I teach 1 million students, you should be able to understand. So thanks for that question. Is there somebody that still has a question? No, it is still that you know, and your question has been answered. So please, you can rub it up or whatever, still showing, indicating the question. Now, we come proper to where we are going. We look at how we can name carboxylic acid, adding to the rules that Professor Shonibaria taught you. We see the following slides. Just 1 or 2 rules. The rules are not many. There are things you can read through and you can get at the tip of your finger. The allopac name makes use of the corresponding alkane with same carbon chain, usually the longest chain with the carboxyl functional group. Like I said, whether you are counting left or right or whatever, longest carbon chain is longest carbon chain. And replacing the E of the corresponding alkane name that have the same number of carbon in the longest chain, you now replace the E of the alkane name with OIC, oic. So, and you make sure, in fact, just like aldehydes, carboxylic acid functional group carbon is always taking number 1, wherever it is. You must take number 1. Even when other functional groups are there, you must first number it as number 1. You start looking for longest chain from there. So other substances are located and named on the main chain. So let's look at this additional rule and also see examples. We have also treated this when I was under carbonized, and we utilized Greek names to indicate positions of maybe some functional group of branchings on the carboxylic acid moiety. So positions of substitutions are ascribed position 2, position 3, position 4, depending or with respect to the longest branch chain of the carboxylic acid. And you utilize the Greek letters, alpha, beta, gamma, delta, omega, and whatever, you know, etc., that denotes this position. Position 2, we know, is alpha position. Position 3 to the carboxylic acid carbon is beta. Position 4 is gamma, and so on and so forth. So position 2 is alpha. That's what I put. So let's look at this example. Look at the compound below. The carboxylic acid is taking number 1. This is number 2. This will be number 3. There's a branching here on number 3. So that means there is a 3-methyl, and the longest chain is 1, 2, 3, 4, 5. Pentanoic acid. Yeah. So that's a 3-methyl pentanoic acid. And the Greek name, what is number 3? Number 3 position is beta position. So you can also call it a beta-methyl pentanoic acid or 3-methyl pentanoic acid. Such questions are cheap questions. You spend less than 5 seconds in the exam, and you pick. You just tell your lecturer, ma, sir, I know people. So you show that. So the next one, we can also have aromatic carboxylic acids, and that's a very good example. Is your benzoic acid. You can draw the benzene ring or show it at C6H5, now bonding to the CH. So aromatic carboxylic acid are also related to the appropriate hydrocarbons. Even though your syllabus will say carboxylic acid, I think what I'm teaching you, I'm not crucifying you, and I'm not doing too much. That's why I don't go sick. And my salary, I use it to do good, because it's better I teach you and you become so strong anywhere you are, and you are a proud graduate from the University of Ibadan. Clap for me. Okay, right. So another good example of the derivative of benzoic acid, aromatic carboxylic acid, is the methylbenzene carboxylic acid. We have talked of toluene that has the CH3 bonded with benzene ring under, I want to oxidizing now to get our carbonate. But over here, you have the benzoic acid already, and either at the auto position or para position, any position, auto, meta, para from the benzene ring, that is the benzoic acid, you can have your methyl. You call that one a toluic acid. It can be auto toluic acid, meta toluic acid, or para toluic acid. Some of these syntheses will still carry out when you are in 300 level. You meet with the 376. Let me give you a little flashback. And everybody take your jotter and be faithful. Don't look at somebody. Know that God's eyes see you, even when my eyes cannot reach where you are there. So give the structure of these two compounds. 2-methylbutanoic acid. Have you written it? Write it quickly. Then the second one is 3-hydroxypentanoic acid. I'm giving you 30 seconds. Ready, you must have finished one. Write it in your jotter. Write the structure. Let your hands work. Let your brain be alert. Don't disturb others. Do it yourself. Download your YouTube after, and you have me speaking to you live all the time you want to hear. So now exchange if you have somebody there, or just get a testifier to mark for you. And not only the structure, you also to give the alternative name. So mark yourself. Who among you got 4/4? Are you sure? So the first one there, which is 2-methylbutanoic acid, the alternative name is alpha-methylbutanoic acid. And you can see that on alpha group, you have the methyl group, and then you have 4 carbon on the longest chain. Then the second one, that is 3-hydroxypentanoic acid, has 5 carbon on the longest chain, 1, 2, 3, 4, 5. And then on position number 3, you have the hydroxy group, 1, 2, 3. So on 3, you have the hydroxy group. So you see, also referred to as beta-hydroxypentanoic acid. Great. Now let's go to another aspect. I can give 1,000,001 examples, but that's just one, whether it's aromatic or alkanoic, whichever. So for the properties and uses, applications of properties and uses of alkanoic acid, let's just go through these 2 slides. The earlier members, the lighter members, that is number 1. Number 1 product we said is methanoic acid. Number 2 carboxylic acid is ethanoic acid. Okay? So number 10 member will be what? Decanoic acid. Great. So from methanoic acid to decanoic acid, they are all liquids at room temperature. Then this is the most common. And why do we call it glacial acetic acid? It's because it is ethanoic acid naturally. We call it glacial acetic acid because it normally freezes. By the time you have 17 degrees C, and at 17 degrees C, you are still, it's like your air condition, something. You see, it's freezing, forming kind of ice-like solid on top of it. That's why we refer to it as glacial acetic acid. Now we have the lower members having sharp pungent odor. Don't bother to smell. You may only use the hand. Look at me, I'll show my video now. When you are smelling, just put hand like this on the bottle and you can now smell the glacial acid. I don't have enough data, that's why I'm not using video. And no money. Government is not paying us. I'm just doing Samaritan work. It's all this my data. I'm buying with my money I should be using to care for my body. Well, lower members have sharp pungent odor. Then the first four aliphatic members, that is methanoic, ethanoic, propanoic, and butanoic acids, are highly miscible with water. That's to tell you that carboxylic acids are, some are polar. They are water soluble, just like their alcohol counterparts, since their functional group is capable of forming hydrogen bonds with water. So the covalency characterizes higher members, high ratio of hydrocarbon therein compared to the COH, which is polar. So to the higher hydrocarbon content. So they are progressively less soluble. As the molecular weight increases, they become insoluble in water. So the aromatic carboxylic acid, that is the benzoic acid, is slightly soluble in water too, but readily soluble in hot water. The temperature is aiding with solubility. So carboxylic acid dissolves in appropriate organic solvent because it's an organic compound. So you should expect that. So most of the things I'm telling you from GS3 students know it. So since your GSS, you should be conversant with some of the things I'm talking about. It's just a build-up on what you know before. Now let's still continue on the physical properties of these carboxylic acids. Their boiling point in degrees Celsius increases with increase in relative molecular mass down the homologous series of compounds, and that is general for any homologous series. As the molecular weight increases, you have their boiling point increasing. For aromatic acids, when they are compared to their aliphatic counterparts, they exist as crystalline solids, having a higher melting point. Even though they have similar molecular weights, when they are aromatic, they are somehow characterized with being crystalline and then having higher melting point. Now, in the aliphatic series of carboxylic acids, the members that have even number of carbons, they have higher melting point than their members that have odd number of carbons. Is that not, is that not funny? Even number, odd number, still plays some great work here. Everybody clap for me. So structural elucidation, utilizing X-ray analysis, show this is related to the packing of the crystals and the solids. You may ignore it, but it's good, especially those of you in chemistry department or that we do chemistry education or whatever up to your 400 level. Now, density decreases with increasing relative molecular mass. Is that not also good? It has unique characteristics. Now, let's go to their formation, their synthesis, or their preparation. And we're going to spend some good time here. Good enough, we still have approximately 1 hour left. Let's take our time, take your jotter near you. We'll be walking ourselves into understanding the synthesis, the preparation, the formation of canoic acid or carboxylic acid. First of all, we will try and consider their industrial sources, how you can commercially obtain our carboxylic acid. Then later we will look at their lab preparation and other synthetic methods of obtaining our carboxylic acid. So for the industrial or commercial sources of carboxylic acids, like I said, there are some of them that are germane. The methanoic acid, the first member and second member, ethanoic acid are germane, and the aromatic benzoic acid is germane. So for these three, I want us to look at their commercial sources. Now, in this one, I want you to look at it very well. That's why I'm elongating it. For their industrial sources, for methanoic acid, you can obtain it by reacting your CO, that is carbon 2 oxide, with sodium hydroxide. That's our caustic soda. At very high temperature and pressure, it first gives you the sodium salt, that is sodium methanate. And then under dilute acid, you have the volume of your methanol acid coming up. So that's the commercial method. It's quite not expensive. It's not too expensive to obtain methanoic acid through this method. Another, okay, the second member, that is the cyanoic glacial acetic acid. You can obtain this in glacial acetic acid, the cyanoic acid. Just remember the carbonyl, the aldehyde, the aldehyde counterpart. It's 2 carbon, and that's ethanol. So easily oxidation of ethanol will give you ethanoic acid. It's straightforward oxidation. And over here we are utilizing this anhydride, ethanol anhydride under this catalyst, manganese catalyst. And you have your ethanoic acid. Then the aromatic carboxylic acid, that is your benzoic acid. You can write it like this. You can also write it as C6H5, like I said the other time. We have 2 methods here for obtaining our benzoic acid. Both methods. Now, that is industrial method. Both involves the use of catalyst. This is a 2-step reaction, while this one is a 1-step reaction. We have vanadium oxide as catalyst at this very high temperature of 550 degrees C. Working on this 1,2 dimethyl benzene, or you say methylphenone, also methylphenone, or you give it a good name. Then you have this intermediate after the catalyzed reaction, being is an anhydride that has the ethyl link to 2 carbonyls. Then, in the presence of organochromium catalyst, you have it breaking up and forming your benzoic acid with elimination of CO2 as a gas. Since it's a gas, it will easily run off and you will commercially and industrially obtain your benzoic acid. Now you have your toluene. Toluene or methylbenzene under this catalyst, saying vanadium complex catalyst at high temperature is also an oxidation reaction. Hydrocarbon oxidized. Definitely it will pass through alcohol, aldehyde, and immediately don't even stop. It will beg you to go straight to the carboxylic acid. So they are quite germane and beautiful. Now we come to the laboratory methods of obtaining them and other synthetic methods. I'm using an X here because good enough, this is the Cannizzaro reaction. We touch it in the synthesis of carboxylic acid. If you say you are going too much, please decide to do that. Or just mention it briefly because of those from chemistry department and maybe I will need it in the near future. So I will leave that last one. Definitely I won't bug you. I will only touch it slightly. Even if I have a slide on it, I will touch it slightly. And once I put that X in red, you may not bother about it. Synthesis or how we can prepare or form carboxylic acid. This one is germane. We are used to it. They wake you up from bed, you should be able to give them. And that is the oxidation of any primary alcohol. If you first get to aldehyde, immediately, no begging, to form the carboxylic acid. Also from the carbonation reactions, utilizing greener reagents, the synthesis will yield carboxylic acid. When you hydrolyze any nitrile, you'll be hearing of CN triple bond. So all these are nitriles. Hydrolysis of the nitriles will yield our carboxylic acid. Now, hydrolysis of esters. Like I said, hydrolysis of nitriles will yield carboxylic acid. Likewise, our saponification method, where you have these are reactions with cleaning visible from primary school. Production of soap, esterification method, opposite of saponification method. So hydrolyzing esters involving saponification, yield the carboxylic acid. Then the last one there will be the Cannizzaro reaction. The last and not the least, is synthesizing the aromatic benzoic acid. Since we are more on alphanonic acid, I started to style it. After I thought, maybe some of you want to report me to my teachers, and I decided I better remove it instead of wasting my energy. Just mention it. So for the aromatic acid, benzoic acid, you can just oxidize the methyl benzene and you obtain your carboxylic acid. So straight off, let's do them one by one and see how far we can go in the next 30 minutes more. So from primary alcohol, you can give 1001 examples now, closing your eyes. So let's just go through the slide together. We have said that common reagent, when you see a reagent, you can say what is the reaction that is happening. When you see potassium permanganate from your secondary school, you know that's oxidation. Those of you that went to A level somehow, potassium permanganate is there. Okay, so if you see potassium dichromate, no, this is the chromium or any chromium products, compound that will yield oxidation of our primary alcohol. First of all, to aldehyde and further proceed with no heat to yield your carboxylic acid. So the trend of oxidation, we have shown it several times. Primary alcohol yielding as the primary alcohol, anytime the COH bond, the carbon is having two other hydrogens, we call it a minimum of 2 hydrogens, we call it a primary alcohol. And then it uses your aldehyde. Like I said, that no one should ask the question. When you write COH, that's alcohol. But when you write CHA, that's aldehyde. And then this will easily oxidize with the carboxylic acid COH. So the method can be used in synthesizing whether it's aromatic or aliphatic carboxylic acid. You don't have to work with head. So I'm giving definite examples because I think you need examples, but you can always write many. We've been doing examples. So that's the general form. Oxidation, instead of O in bracket, I can put KMNO4 or any of the chromium compounds. And you have ethanol, definitely giving ethanol, and then ethanol. This is propanol, giving propanol, and then propanol acid. If I started with something like ethanol, ethan 1-or, ethan 1-or, because this time it must be a primary alcohol. Ethan 1-or, we give ethanol, and then finally give ethanol. Just, you can give yourself quiz in your department by department, class reps, form tutorial groups and deal with all I've been giving you tutorially, department by department. And keep giving me feedback. I don't know. I'm not a newscaster, but next week we still have it this week because it's not likely the government asks you to come back for physical lectures. I think we are used to this. I think we better finish up. Better I finish up lectures, and then we go to my impromptu test too, or project or anything. I will start introducing that to you to get set. Carbon 4 oxide, that is the carbonation of utilizing greener reagents. You can use that in synthesizing our carboxylic acid. So over here, you have your Ca2, that's carbon 4 oxide, that is being bubbled into any greener reagent. You just take cognizance of the structure of your greener reagents. Just close your eyes and you'll be able to predict the product over here. Very simple. So on treating the greener reagents with dilute acid, you produce your aliphatic acid straight up. Very, very straightforward. Only over here, take cognizance. Okay. Before I go to the examples, to prepare aromatic derivative by this method, in fact, benzoic acid derivative, the solid carbon 4 oxide, we call that one dry ice, instead of utilizing gaseous CO2 for aliphatic carboxylic acid. For the aromatic one, we make use of the solid carbon 4 oxide dry ice. I used it a lot when I was in IT doing some work in their laboratory. Because of the condition, dry ice. This one reacts with aromatic derivative of greener reagent which also serve to cool the reaction. So I see that the temperature is so low. Maybe that's why I cannot afford it. Now let's see the examples that I have here. Greenhouse synthesis involving carbonations. Let me return back to what I have. Okay, let's see if I can push it up. Let's see if we have it. Okay. I hope I'm not spoiling this. Okay. Okay. I'll be doing it after the class. Let's see the effect of what I have here. The greenhouse synthesis involving carbonations. So you can see your greenhouse reagent. Let's first check on the general thing. Anytime you are making use of greenhouse reagents, we did it during ISA, and I said it must be under dry condition, very perfectly dry. So you have the intermediate, which the second reaction, the second step of the reaction, you are trying to do one and then two. Or they split it into two equations like this. So under acid hydrolysis, you have the yielding of the carboxylic acid. You will notice that from the greenhouse structure of the greenhouse reagent, there is an additional carbon. That's what I want to say. Why I was trying to pull it here and there. There is an additional carbon. So depending on what you started with the greenhouse reagent, just add an additional carbon that can predict your carboxylic acid, especially for exam purposes, interview purposes. So look at this greenhouse reagent. What's this greenhouse reagent? That's an ethyl magnesium bromide. And look at you are coming up with propanoic acid. Because you started with ethyl 2 carbon, you are ending with an additional carbon, which is prop 3 carbon system. The same thing to the aromatic. You have phenyl magnesium bromide, giving us your benzoic acid. The benzene group, see outside the benzene. So it's quite simple. Now from hydrolysis of nitrile, here the first thing is the formation of the nitrile, or especially if it's not prepared before. So you first form your nitrile from reaction of your haloalkane with alkali metal cyanide, nickel, alcohol, which is a solvent that can dissolve both of them. So through hydrolysis of the nitrile formed either in alkali, give the carboxylate an ion, or in other words, the nitrile can hydrolyze a mineral acid to produce a free acid. We see a few examples of this. There is intermediate formation of amide in these two cases. Look at this aromatic nitrile, C6H5Cn, which is our benzonitrile or benzene carbonitrile. Hydrolysis of it is capable of giving the benzoic acid. Let's see equations that I have. Yes, it looks like yam. That's why I'm trying to put it in a better shape. Don't mind me. Chemist, what is more important is that I'm passing knowledge. I'm not really, and you can see that is the first time work. I spent nights getting this ready for you. Clap for me where you are. So the idea I'm trying to bring out here is that you have your haloalkane reacting with your prepared nitrile. So you can see on this slide that you have your haloalkane reacting with sodium cyanide, which is our nitrile. Under aqueous alcohol, you have the production of your nitrile. And it is now this nitrile that hydrolyzes to give the carboxylic acid. I'm supposed to have given that one, so don't mind me. So you can easily do that. An arrow from here down there to give RCOH. And just like the greener reagent too, you see that the structure of your haloalkane, just add 1 carbon to it. That is what will give you your carboxylic acid. Look at a vivid example over here. You have your propyl chloropropane. Chloropropane with sodium cyanide in aqueous alcohol. Alcohol here is methanol. You have the nitrile, which is already having 4 carbons in them. Hydrolysis of it first form the amide, which I said earlier here, that there is intermediate formation of the amide in both cases. So we have the intermediate formation of this amide, CONH. In fact, the primary amide there is part of the derivatives of carboxylic acid we're looking at. And then you have the ammonium salts of the carboxylic acid. This is an aromatic nitrile, and just mere hydrolysis, one-step reaction. You have your benzoic acid from there. Let's look at another method, and that's from the hydrolysis of esters involving saponification. Over here, what is germane, or what's the chemistry? What is happening here? I'm going to give you a good example. Over here, you reflux your ester. You all know what esters are, good smelling systems. RCOR prime, where R and R prime could be the same or different. So you reflux your ester in concentrated sodium hydroxide. My father's senior sister used to make soda. In fact, they had a Iodoform, and before I was born at all, she's been selling soda in the whole of my hometown, and you can be sure they know a lot of chemistry. That's why I said you have been learning most of the things I'm teaching you from your primary school, not even from pregnancy. So refluxing esters in conc sodium hydroxide and treating them in dilute acid will yield our carboxylic acid. Let's see a good example. Okay, I can change R and R prime. That's the ester, generally, put specific things there. And then under your soda, sodium hydroxide, your alkali, you have the sodium salt of the acid. Ordinary hydrolysis in acid yields our carboxylic. You will notice that the same number of carbon you start with is what you are ending. Those are the germane things I feel like telling you in my course, so that you are not carried away. That's why some people, when they attend my class, they score 90, 95%. I don't know. It's because you people will not log in on time, or you'll still be parasitically logging in with some other people. Be yourself. Get your notes near you. You will not be confused in my own class. I can bet it with you at any level. So let's move to this other one, which I say germane, but many times some people think is a difficult aspect. But if you go and what is Cannizzaro reaction known for? We're coming back to that 245 slide. Can you see how many slides I prepared? Just for you to, and they are eligible enough. So clap for me where you are. Anytime you have Cannizzaro reaction, you have the formation of both the reduced product and the oxidized product. This is aldehyde. What is the reduced product? The reduced product will be the alcohol that forms. And then the oxidized product of aldehyde will be the acid, carboxylic acid. So in Cannizzaro reaction, we utilize alkali. Under strong alkali, it gives both reduced product and oxidized products, not that carbonate that started it. And you can, even in aromatic system, you have this aldehyde, para-nitrobenzaldehyde, under that strong base or alkali, you have the reduced product, the para-nitrobenzyl alcohol, reduced product, and then you have the oxidized product, which is the sodium para-nitrobenzoate, the sodium salt of the acid. So that's all about Cannizzaro reaction. It's not a difficult reaction. Generally, in Cannizzaro reaction, let's go through the slide together. Generally, in Cannizzaro reaction, an aldehyde that does not have, I wish you can make this germane, that does not have alpha hydrogens. Let me make it red so that you will know that it's important. Important and germane condition for the Cannizzaro. Apart from that, it yields the reduced and the oxidized products, so that you see it very well. I'm enlarging it. Just try to save. Okay. So when you have an aldehyde that does not possess alpha hydrogen, when it reacts with this soda or sodium hydroxide alkali, in the reaction, half of that starting material, the aldehyde without alpha hydrogen, is converted to the oxidized carboxylic acid, and the other half is converted to the alcohol. So you have 50-50%. So hence, in Cannizzaro reaction generally, you have both oxidation and reduction products being formed or produced. So that is when aldehyde reacts with concalcali, sodium hydroxide specifically, it gives both reduction product, alcohol, and the oxidation product, which is the salt of the carboxylic acid or the carboxylic acid. So aldehyde that does not possess alpha hydrogen, like your phenol does not have an alpha hydrogen, your benzaldehyde does not have an alpha hydrogen, all this one will easily undergo Cannizzaro reaction. It's a very direct reaction. Can you see your methanol? If I only one carbon there, so no alpha carbon, talk less of alpha hydrogen there. And even your benzaldehyde, the alpha position number 2, this has 4 bonds already, 1, 2, 3, 4. So no alpha hydrogen. That's why it's capable of forming this. And I'll just look for molecule, either with branching or whatever, that doesn't have alpha hydrogen. Don't expect these questions in the exam, even tests. And I ask you to predict what are the Cannizzaro products, or what's the, I won't even call it Cannizzaro. Once you put potash there, sodium hydroxide, should be able to give the reduced and the oxidation products. Now we are nearing the end, and that is after their preparations, we now come to the reactions of these acids. The reaction, I've said it summarily. I even have 3 of them stadia that we don't need to do everything. In fact, 1 or 2 is okay, but these are things you are used to. You know, esterification reaction, huh? You are used to it. Salt formation, I'm sure you know it. When we come down and you see that there are things you know before. I'm just building up on your past knowledge. Then conversion to acyl chlorides of the carboxylic acids, and these are great derivatives of carboxylic acid. Amide formation is also a derivative. So as we are treating them under carboxylic acid, I'm also treating them under derivatives of carboxylic acid. For instance, these are ways of preparing some derivatives of carboxylic acid. So it's like 2-in-1 lecture I am doing. I hope I'm not rushing you. Okay, so there are some questions in the air. What are your questions? Anonymous participant, you better don't be anonymous. Start talking, start being yourself. Anonymous participant, give me your name, or else I can deal with you. God sees you. He says, what is an, it's not a alpha hydrogen. It should be an alpha hydrogen, because that's simple English, primary school English. What's an alpha hydrogen? Alpha hydrogen means it's on position alpha. We have talked of the Greek word alpha. Alpha position is position number 2. So go to your position number 2. That is it. So I'm answering it live. Is that okay? I've answered it live. That it is an alpha hydrogen is the position number 2 hydrogen. You now said it's not there. Who are you? Sileski Junior. Are you just coming to the class? You are raising up your hand. Don't disturb this class. There's another Sheye here. Yes, Sheye. It says, please, ma'am, what is an alpha hydrogen? Oh, right. Same question. I do not get the explanation. How do I recognize it? Yeah, you should have gotten it by the time I explained to the anonymous participants here. Sheye, the alpha hydrogen is the hydrogen bonded directly to carbon number 2. When you are considering if it's carboxylic acid now, carbon of the carboxylic acid is 1. So the next carbon to the neighboring carbon, if it has hydrogen, we call that hydrogen alpha hydrogen. Now, for Cannizzaro reaction, it must not possess alpha hydrogen. So you can easily say that. Is that okay? I think you should clap for me, Sheye, an anonymous participant. I've answered your questions. So who is this hand raiser? Hand raiser, I don't know you. Okay, let the hand raiser not disturb us. Now, let's pick on each of these reactions one by one. We have the salt formation. Everybody says salt formation there. Can you stand up and jump 3 times? so that it won't be that you've been sitting down a long time. If you ask me to teach you for 5 hours, I can do that and you won't be tired. But let me just stop after the second hour. We are nearing, we just have less than 30 minutes to leave. So in the salt formation, this is an indication of its acidic property. You said, in fact, the name depicts carboxylic acid, its acidic property. So this reaction with Germain showing, demonstrating our carboxylic acid acidic property. So what happens there? On reacting our carboxylic acid with metals, the carboxylic acid liberates hydrogen. That's why I said you know it from secondary school. Test for acids. We say react it with maybe the salt of that acid. You react metal with the salt of the acid, and you hear some effervescence noise, evolution of hydrogen. So it also gives off CO2 when you add the acid to sodium carbonate. You do it a lot in your qualitative analysis at O level. Even sodium bicarbonate to NaHCO3. You have effervescence reaction showing the evolution of CO2, and you start testing the CO2 with lime water, you recall. Now with sodium hydroxide, we have our carboxylic acid forming salts and water only. That's salt formation. So all above salts can regenerate carboxylic acid just by reacting them with mineral acid, HCl, H2SO4. You easily have that. Let's look at some examples here, though general, but these are salt formation reactions. Definitely don't expect this in the exam. I will change my R's to some specific things that you will now use your common sense to depict, or rather predict what will happen, what you expect. So under the reactions of carboxylic acid and salt formation reactions, the one with metals, like we said, the metal here is magnesium. Magnesium is reacting with our carboxylic acid to liberate our hydrogen, like we said, and you have the magnesium complex being formed. Then with carbonates, sodium carbonate, sodium hydrogen carbonate, you have the liberation of CO2 effervescence reaction, and then well, aqueous, but let's leave it like that. Then reaction with our soda, our sodium hydroxide, our alkali. The carboxylic acid reacts with sodium hydroxide to produce the sodium salt of it. And then from any of them, RCONA, can see any of them, just react with any mineral acid. That's a method of also preparing our carboxylic acid. It's another synthetic method of preparing our carboxylic acids. Now you're very, very used to reaction. If you wake you up from bed, what is the esterification reaction? The reaction of carboxylic acid with alcohol to produce ester and water only. And when you come to inorganic reactions, we call that one what? Neutralization reactions. So recall your mechanism of formation of esters and water only. I put your only because that's the German word in O level. From reacting carboxylic acid with alcohol involving alkoxy hydrogen fusions. And you can always represent this anywhere T. I have some specific, you know where the water only is coming up from. The OH of the alcohol and the hydrogen, the OH of the carboxylic acid and the hydrogen of the alcohol is what is responsible for our water. Let me see if I can elongate it without disturbing. The O is not showing very well. I pray it shows. If it doesn't, just know that that is H. That is O. Sorry, H2O. That is it. Let's just leave it like that. So now, even when it is aromatic, that is benzoic acid, you have this OH taking off this proton from the alcohol, methanol, and you know how to name them now. In fact, under esters, you should be able to name this. You have the First name your alcohol, poetic, ending with YL. Then you end with OACE, that is naming of esters of the carboxylic acid. So this one that has ethanol, ethyl, then the carboxylic acid is propanoic acid. So this will be an ethyl propanoate. That's the ester. So here we have benzoic acid and methanol. So that will be a methyl benzoate. That is the name of that ester then. Good. So we're learning many things inside a single class. So give the names of the ester and salts. Good enough. I've done it in the classroom. And I've given a rule I didn't even make slides for. Okay, I hope I'm not getting tired myself too. So we come to another reaction of acids, and that is how we can form inside chlorides or acid chlorides from our carboxylic acid. You will see the equation example there. Let's go through the slides. These are common reactions. Everybody say common where you are. Yes, they are common reactions. You don't have to frigid, you don't have to run away. These are common reactions of both aromatic and aliphatic carboxylic acids. Over here in this reaction, we have the hydroxy group of the carboxylic acid easily being replaced when it reacts with phosphorus trichloride, PCl3, or phosphorus pentachloride, PCl5, or what we call cyanide chloride trivially, or sulfur dichloride oxide, that's SOCl2. All these are chlorinating agents that makes possible the acyl chlorides, and it yields our acyl chloride, so, or acid chloride. So when you react with SOCl2, which is the most appropriate here, since the other two products are gaseous and can be removed from the reaction. So the reaction with SOCl2 is most appropriate since the other two products are gaseous and can easily be removed from the mixture. Let's check on the reaction. That's it. This is the most appropriate one because HCl gas and SO2 gas. So you have 100% of your acid chloride or acyl chloride. Unlike here, this could be aqueous and whatever. So the mix of you have to pass through some chromatographic methods to separate and get your acid chloride. So what with PCl3 or PCl5, you have this formation. So all our target is acid chloride over there. So you can have that. Vivid spirit. Okay. So over here, when do you want us to meet again? That should be, no, it's Monday. What is Monday? Is Monday convenient? Governors and class reps meet together and give information. The Monday lecture is supposed to be when? 4 to 5. Maybe we cancel Monday lecture. That time looks odd to me. It's supposed to, looks odd, except we can bring it to morning section. But instead of over-rushing ourselves, why don't we meet on Tuesday? So we meet throughout next week, Tuesday, Wednesday, Thursday. So I'll be prepared for my impromptu test and whatever. By whatever means, I'll communicate it through elements if need be. So we come to the amide formation. I will start listening to your questions after this amide formation, and that's on the reactions of our carboxylic acid. So let me say straight off that at quite high temperatures, you have your ammonium carboxylates being formed. How? When you react the carboxylic acid with ammonium carbonate, you have your ammonium carboxylate. So the ammonium carboxylate is capable of going through dehydration in the presence of the free acid to yield our amide. Now, the free acid is important because it is, in its absence, the ammonium carboxylate dissociates on warming. So the free acid first form helps to maintain the direction of reaction. So you have it there. Also make this alignment before I unmute you and you can ask further questions. You can now talk. So you can have the formation of your amide from its reaction, that is the ammonium carbonate reacting with our carboxylic acid. I even have balanced equations throughout. Though in the exam, don't expect arrows. Like I said, yeah, could be methyl, ethyl, those simple moiety, and isopropyl, or a little branched. Just don't reject, still have it there. Somebody say something. Oh, what is this thing? Wow. No. Ah, what is this? I think I touched something not too long. Are you seeing my, will it be that, what's happening? This my research for Cannizzaro reaction, the oxidized and reduced product are formed. It's a kind of, is it a redox reaction? Yes, anonymous participant is a kind of redox reaction. It is. It is. Yes, who is this person raising up hand? Is there another question? No, but are you seeing my board? Let me just make sure. Oh, I hope these materials are not getting heat. What is happening? I hope you are seeing I'm sharing my screen with you. No, I'm not too sure I'm sharing my screen with you. Am I sure? Just the question answer thing. One of you should just write. Are you seeing my screen? Are you seeing my screen? Once you are seeing my screen, I can always move on. Over here, we're already there. And like I said, ammonium salt, you can see the hydrolysis, the ammonium salt, and the free acid is being released. The free acid has the role, like I said. My internet connection. I'm using Smile, and you know how much money Smile is. I don't know why it is fluctuating. I just pray it's not finished because that means no money to recharge. So we have said that the free acid is very important because it's the one that helps, in its absence, the ammonium carboxylates we started with dissociate on warming. So to prevent that dissociation on warming, I've even put it on it, dissociation in absence of free acid. So you need your free acid to prevent the dissociation of your carbonate. So you have that. Yes, let me unmute you and listen to some of your views. We still have some good minutes. Can you stretch? Just stand up and stretch your body. Yes, okay. I have a lot of chats here. No problem. All chats. I've seen your chats. I'm coming. I will soon start unmuting you. I'm trying to see. So, like I said initially, I have the link, the YouTube link then, so you can easily have that too. Now, anonymous participant, please smile. Yeah, it's a redox reaction. Okay. Sarab Okpeyemi, the screen is visible. That's good. Thank you very much. Anonymous, participant, give me your name. I don't want anonymous again. Yes, ma, that's good. Anonymous participant, good morning, Prof. Your class has been broad and comprehensive so far. It will be much more appreciated if you can give us a hint of how your test and exam, you want to do giraffe 419, exam questions will look like, so we can read smartly. Start reading smartly from now. Thank you in advance. No need of thanking me in advance. I will do the normal. Just come to my class and stop using anonymous participants. Give me your name so that I will record. No problem. We also, by the time I'm ending, especially towards after your final test or the final time, you have to give a little composition, just like a paragraph of what I like and what I don't like about Professor Morokola. So, and probably try to submit it to me on your paper. Don't bother to write your identity through your class reps, but that's going to be a long time. You don't have to start deciding who I am now. Let's face it, if you think I'm good, no problem. If you think I'm bad, no problem. So let me start unmuting you and listening to my big people. I hope you are enjoying home and you are enjoying your chicken with your parents. Okay, Favor Oluwayomi, unmute yourself. If I don't call your name, don't unmute yourself. So Favor Oluwayomi, unmute yourself and.
Good morning, ma'am.
Yeah, good morning, Favor.
Maybe concerning the aromatic structure for the Cannizzaro reaction, please can you go over it again?
Why do you want aromatic structure? Benzaldehyde derivative.
Okay, sorry.
It doesn't have, okay, it doesn't have alpha hydrogen. Is that what you, no problem. I can go through it. I can go through it. Somebody's already, you don't have to wee because I said, you don't have to wee in your pants because I said you will have test. Somebody is already saying, ma'am, is our test going to be online or physical? You have to be wee. Don't worry. It's impromptu. You don't have to predict my test. Is that okay? So let's answer that chap for now. Where is Cannizzaro? Cannizzaro, where are you? Let me see where I have it. Okay. Don't unmute yourself. I think this is what, no. This is Esterification. No. This is our Cannizzaro. No. Okay. It is the method of producing. Yeah, they're coming there. Cannizzaro is like 1, 2, 3, 4, 5. The fifth reaction there. No chloride, no nitrile, not hydrolysis of it. Yeah. So I said unmute yourself and stop being a naughty chap. That person talking underneath. Now this is the aromatic side. You will see that in this benzaldehyde derivative, that is para-nitrobenzaldehyde, this is position number 1. And then this is position number 2. On this position where I have my cursor, there is no hydrogen there, which is a very important condition for Cannizzaro reaction. It does not have alpha hydrogens. So the same thing too for the first one, methanol. Methanol is even having 1 carbon. But I can give you other aldehydes that have position number 2 with branchings and no hydrogen on it. What is more important is no hydrogen on it, so that you can form both the reduced product, alcohol, and the sodium ester, which is the oxidized product. That's all. Yes. Let me call another person, or if the screen is clear enough. Thank you. I like the way you teach, ma'am. I don't worry. Anonymous, good morning, ma'am. I wanted to ask if you can make the slide. Why not go to the YouTube? I'll give you something. Let me see, are there some other hands that are raised up? Okay, let me go to your attendance and see hands that are raised up. Okay. Okay. Yeah. Yeah, man. hands. Or you put it under question and answer.
Yeah, listening.
Yeah, the question and answer. Ma, please, can we have a comprehensive slide of all topics you are teaching? What kind of comprehensive? Go to textbooks. You have the YouTubes. Just sleep on your bed. Keep enjoying your jollof rice and you'll be listening to me with the YouTubes. So what else? Come to library. Get to library, any good library, anywhere you are, get a university and get the library. Get organic section, organic chemistry section. I'm trying to look for, let me check on questions, okay? Good. Let me leave chat. Let me come for questions, okay? Have I answered all questions? Okay, Olatunji is a present, not you. Olatunji Olushola. Please, ma, can I get the link for the YouTube? Captain, Governor, give them on your, I've given you several times. I like the way you teach me. No, as I didn't, let's leave it. Any other question? iPhone, who is iPhone? Put your name there, please, ma. Can I get the link for the YouTube? Go to your governor. He has it on your classroom. Olatunji, past question too easy. 176 past questions too easy. No, ma, your slides are the one we want. Your slides are the best. Naughty 176 past questions too easy. Naughty one. Money, ma. Is carboxylate anion reversible? Anion. Yeah, if you place an H plus now with sodium, it picks it up. You know. No, ma, your slides are the ones. Please stop that. You can read on our own. Okay, any other tangible question?
Yeah.
Unmute yourself if you have a question, a reasonable question. If you have a reasonable question, just unmute yourself. Who told you iPhone is saying because it's bulky? Who told you it's bulky? Is it because I decided to use so many slides? It's so that it can be visible and good. I can use just few slides for each homologous series and boom, I leave you to your problems. I want you to understand what kind of bulky. Get to textbooks and stop being lazy. Good morning, ma. Is carboxylate ion reversible? Yeah, I've answered that one. No, ma, your slides are. You want your slides are the best. Who told you? Get some good textbooks. Yes, good morning. Who is that naughty boy that is saying Arin Kaka? Your voice like voice of a fast person. Unmute yourself immediately. Very naughty. If I catch you. Yes, somebody with reasonable question there.
Yes, ma, also ask, ma, is alkanoic acid, is it a redox reaction, ma?
Is it the preparation you are saying? The Cannizzaro reaction. The Cannizzaro reaction is the redox reaction because you are having the product. Yeah, it's similar. That you have both reduced and oxidized product. But what is it to react? You are just reacting with high concentration of sodium hydroxide.
It cannot come out.
Who is that person say it cannot come out? Is that a question? I said once you don't have a reasonable question, don't unmute yourself. Hello.
Good morning.
Who is this one? Yeah, good morning, my lady. Talk now.
Good morning, ma'am.
Yes, good morning, my brother.
Reaction. Is it reverse?
Which one?
The Cannizzaro reaction.
I think I made it straightforward. It's forward reaction. Forward ever, backward never. Once I was past questions too easy, go and give me your name. It says, please, I want to ask if your questions will be as easy as past questions. Do you have past questions? Who told you you are a 419 person? Eh? Yeah. I don't know how easy it will be. Any other reasonable question before I say good morning? We have either 1 or 2 minutes more. Yeah, it's exactly 11. I'm sure you have another class maybe. So we call it a day until Tuesday next week. Do you like that? Everybody unmute yourself and say thank you.
Thank you very much.
Thank you so much, ma. God bless you, ma. God bless you, ma. We love you, ma.
You come back to UI.
Thank you, ma.
Your class, thank you, ma.